an explanation of why you can essentially solve for the underlying attenuation coefficients in your image, given that you have measurements that are proportional to the sum of those attenuation coefficients. And so we took sums in the horizontal direction, sums in the vertical direction. We found that that wasn't enough, actually, to solve for each one of the values. So we took a sum across the diagonal, came up with this set of measurements, essentially, which is, we've made these measurements. Those are floating point numbers on our detector. And we know they're proportional to these sums. And therefore, you can solve for what these are and solve for the image. Okay. However, it becomes a problem that is much too big, like for even a modern computer, because these have noise and uncertainty on the measurements do have noise and uncertainty on them. And so the matrix, this matrix that you would invert to solve for all of the mu values in a 5 by 12 by 5 by 12 image, that's a lot of mu values, right? That's 262,000 mu values. So you have a matrix that has that many rows and that many columns. So it's a large inversion problem. It will be done one day, I'm sure. However, given the noise on these, you would have to do some kind of least squares inversion, like the most probabilistic inversion, and so you end up using an iterative technique because of the noise. So we can do another or try another method for reconstructing from our projections. And this is called naive back projection or simple back projection. And if we have an image, now we've graduated to a 3 by 3 image. It has a value of 3 in the middle and 0 in the background. And so what do our projections look like for this image? Let's say we take, looks like we've got 6, 7, 8 projections, right? So we've got one projection across here. Our measured value is going to be 0 because they're all zeros. One projection across here, the measured value will be 3. That's how much attenuation occurred, etc. The thing we don't know for this projection, for instance, we know it all adds up to 3, but we don't know where to place the various weights or values. The 3 could be in any one of the boxes, or we could split it between, a 2 and a 1, etc. So naive back projection, what it does is it says, well, let's take these measurements, these guys, and we will back project them across the projection, and we'll just divide up the attenuation evenly across that direction. Okay, that's our best 0th order guess as to what those values should be. And so when we do that for this, if we project in this direction, right, we'll just say, I've got a 0 up here, so I'm going to project back 0 everywhere. I've got a 3 in this row. I'm going to project it back as a 1, 1, 1, evenly distributed, because I have no other information. I just know it's total, right? And then I'll back project this 0. And then when we go to back project the measurements on this diagonal, we know that it adds up to 3, so we spread that over the whole projection. So we put a 1 in here, we add 1 to here, we add 1 to here. So that gives us 1, 2, 1, because we already had a 1 in the middle, had a 0 in the corners. And when we project on a vertical direction, right, we see we'll put a 1 here, add 1 here, and a 1 here. And that gives us essentially a 3 in the middle. And then on this diagonal, we'll put a 1, 1, 1, and it's a 4 and a background of 1. And so with this very naive use of a selected number of these projections, we achieved an estimate of what the image is. It's not bad. I mean, it's got a bad background. It doesn't, this is a background of 0, this is 1, but it's same basic shape. And this is the peak, right? So that's not so bad. If we do that with many more projections, let's say we now take many views um, and back project those. Let's see what that outcome looks like. Here we have in the plane, we have a disk. The projection of a disk looks something like this, right? And as we change the angle, the position of that projection of that disk moves on our detector. If we naively back project these three projections, we see that we get a peak at the location where that disk is, but we get these artifacts in the background. That's not really what's there. We don't have a star, we just have a disk in the background. But if we do more and more projections, as we saw with this silly example here, the background fills in, we get a filled in background, which is false. I mean, there's signal back here in our reconstructed image, but there is none in reality. And the disk looks something like this. It looks like a very fuzzy, blurred version of the actual disk. And so we've lost some spatial resolution. Something's gone wrong with the way we're combining these data to create a picture that has this kind of fuzz in the background. I'm going to go just for a minute. Trim this arrow. Make sure. Okay. Here's a couple of things we wanted. We did not do this last time. So we got to here. Remember, we have these projections through the patient, measurements on our detector. We transform the actual measurement that we get on the detector, which is ID, and we're going to transform that by dividing by our air scan, taking the log, and then we get the sum of the mu values through that projection. Our job is to go from these measurements that we've taken off of our detector and go back to a picture in the plane of mu xy. Let's look at a simple object, and we'll look at what the projection of that object looks like. So a very simple object is a circle in the plane with nothing in the background. If I look at projections from above through the circle, right, I will get a function that looks something like this. And that is when I'm going through the thickest part of the circle, it adds up to a high value. And when I'm going through a side thin spot, it's a lower value. Given the fact that if we assume the circle has uniform attenuation, say the amount of attenuation is uniform, it's a disk of water or something like that, we know that the attenuation is just going to be proportional to the distance through that circle along that projection. And so when we take this angle, we can compute actually analytically what this curve, which is the projection, would look like, right? So, and this is, you can do this at home, all you're changing is the bounds of the integration. They're going from this top circle to this bottom half circle, and you encode that as the boundary for this integration down here, and you're just integrating one, right? So we'll say the signal here is 1. And that gives you this function for GL theta, which is pretty cool. When you think about it, you say, oh, okay, now for CT of a disk, I know precisely what the actual ground truth data is for that projection. And this is true for lots of shapes. So you can make mathematical phantoms out of circles and ellipses and other nicely behaved shapes, such that all of your raw data can be written down as analytical equations, right? Sort of continuous equations. So now you know the precise ground truth for this set of ellipses and circles you have on the page. And a number of phantoms use this to their advantage. And by the symmetry of this thing, you know that every angle this is what the projection looks like, right? We just rotate it around. It's exactly the same. What was the other thing about this? I think that's it. So here's our line integral, right? We get our measurement at D, air scan, times the attenuation through the path length. Log transform that, and we get this new function, which is called our projection data, or we're going to see it's called our sinogram data, which are just the sums of these mu values. Okay, we did this. So here's a more complex looking phantom. Granted, it's again a set of disks, right, in a geometric pattern, but the projection, obviously, through this as a function of angle is more complex than what we saw with the last single circle. So this is called a sinogram, and our detector position is along here. And so remember, we had about 1,000 detectors along that direction on a CT scanner. So we can divide this up into about 1,000 measurements this way on that order. And then what we're going to do is we have that projection function, and we'll plot that as a one-dimensional brightness. And then we'll stack a set of those functions on top of each other as we go from 0-degree projection all the way around to 180 degrees projection. So when I stack all of those 1D functions, I get a 2D function. It's now as a function of L and theta, which is our projection angle. And then the raw data, or the projections for this object, looks like this. So now it's much more complicated, right? Writing down an analytical function is possible for that because you know the position of each circle, right? And you know its diameter. So you should be able just to write down the actual analytical function for this. If we perform that simple back projection, right, that is the naive back projection. So we just take a single projection and project it back onto the full field of view from which our phantom came or our phantom exists. And we change the angle and just keep projecting those things at different angles. We're going to wind up with an estimate of the object that looks like this. And this is called a laminogram. And when you write down the equation, it looks like this. It's just the sum of each one of those projections, which is this image here. But it just, as theta changes, right, this image just clicks around and it has a different look to it. But we add all those up from 0 to pi, every angle. We just add them up, and this is what that thing looks like. Okay. You can see the background is wrong. It's not 0. It's got a background value, and it's very fuzzy and blurry, right? I put in the lecture materials under files, and then under the CT, technical lecture. See, I put in a MATLAB program. It's not called Radon Demo. I forget what it's called. Let me go take a look for it. It's under files. And then if we go to lecture slides, and I think it's here. Yes, Radon Demo impulse points. Okay, so this is a really simple MATLAB program that you can download and noodle around with to look at sinograms. And so I would encourage you to do that. Just bring it up, take a look at it. Here's the code. It's like trivial. If you feed this to ChatGPT and ask it to make more comments, it will. And it will suggest, hey, do you want to look at different kernels and blah, blah, blah. So, but what this does is it just makes a very simple impulse image, and we run it. Oh, no, didn't like that. Let's add that to the path. Oh, I know. Yeah, I renamed it. Okay. So here's our starting image. It's just a series of dots in the plane, right? So if I look at one of those dots, there it is. It's a peak with a couple of things leading up to the peak. And then here's the raw sinogram data from this data, and I've added some noise onto it. And so this, when you do the essentially transform, the radon transform back, the inverse radon transform of this data back here, it gives you an estimate of what the image would look like if you have this noise on it. And so that this becomes this, right? And you can try different things, right? You can try, let's see what else we have here. If I wanted to say, well, what happens if my first projection angle is 0 degrees, my last is 180, and I'm only going to image like every 5 degrees, right? So let's do that. It makes a new raw data set here. There are fewer of them because I think I had 360 measurements on the last time, and here we've only got, I don't know what it is. But now you can see here's the original image, right? It was those boxes. Here's the image with noise on it if you only take a small number of projections, right? And so the object itself is kind of just decreasing into the background. The noise is dominating the signal. So the delta theta of 5 takes you down to 180 divided by 5 projections, which is not that many projections, right? We can also, say we do a projection every 1 degree, but let's do this. Let's say, for whatever reason, we only gathered up 90, right? So we only went from 0 to 90 projections. Let's take a look and see what that image looks like. Just run it. And this is what the raw data looks like. Oh, actually, we should make the peak signal to noise ratio, which is here. Let's make it 5 so that we can actually see the data. Okay, so now the noise is down here. Our beginning projection or our original data looks like this. It's just this box, right? And then here is what it looks like when you try and reconstruct it with only 90 degrees of views, right? You're missing some information, and so you get these streaks around these small delta point objects. And you could mistake this for structure, right? Which can happen in CT. So this is just a starting program to get you familiarized with essentially the radon transform in MATLAB. And given the radon transform, you can do a lot of simulations of motion, signal to noise, different kernel structures, spatial resolution, whether or not you can separate 2 points, whether or not the Hounsfield unit is conserved under noisy conditions, etc. So that is that. Okay. So let's look at a sinogram for an object that looks somewhat like a human, although this object, again, it's just a series of ellipses, right? So I've got a major ellipse. I've got these ellipses that are bright like bones, like ribs, right? I've got 2 ellipses or circles in the actual body, and then a background, and then a very low contrast structures, etc. What does the sinogram look like for this? Well, this is it. So this is the detector position along here, and this is the angle theta, okay? And so you can see each object in the sinogram, this is why it's called a sinogram, actually paints out a sine wave, right? And this object here paints out a different sine wave. I don't know which one's which here. The big object itself, right? You can see if I project in this direction vertically, it's going to spread over the entire detector almost. And then when I project down onto a detector that's over here, my source is here, I'm projecting this way, it gets thinner. So this is tucked in here. So that's that projection angle. You can see some other projection angles. For example, when we're projecting such that we're looking straight down through both of these and they overlap, That would be right here. Now they're overlapped. So I'm trying to give you a notion of what the sinogram is and what it looks like. The interesting thing mathematically is that I've got the same number of numbers here as I do here. Let's say I have 512 by 512, just for grins, and I make a 512 by 512 image. It's equivalent, the information sitting in this image versus the image here, right? So it's just a set of numbers here, set of numbers here, and they actually have the same amount of information in them. That information is organized differently over here such that it actually is a picture of a human being, which makes it much more useful than this information, right? So if I look at that position, I know, or I just told you the answer. So the question here is like, which one of these, angles of the detector is that data obtained at? So this here, right? It's a sinogram at a specific angle. Okay, we know because it's got narrow waist here that it's either this one or this one, right? So the projection is either down this way or back this way. Let's say this is the origin. This is detector 1 to 1,000, detector 1 to 1,000, detector 1 to 1,000. So the question is, which one of those, B or D, is it? If you look in the background, there's this crap back here. This is the patient table, actually. And then you look back here and you say, okay, well, along my detector, all this junk shows up over here. So I'm going to call this B, right? That's how you figure out which sinogram angle you're looking at. Okay, we can do some other things. So we can take that sinogram for each one of those functions, we back project it, and we get this crappy picture. Okay, it's a picture, but it's not a great one. What we have to do instead in CT is we take our projection data, right, and we look at it in Fourier space, right? We take the Fourier transform of this data, and so it gives you spatial frequencies as a function of position along here. And then we take those spatial frequencies and we multiply them by what's called the Ramlock filter or a ramp filter. And so that changes these data by multiplying by this. So we actually multiply by a 0 at the origin, right? And then amplify the relative power, relative amount of higher frequency data as we move away from the origin. Once we've taken that product and the inverse Fourier transform, it's called filtered back projection, and it will give us the data that we should use to make the back projection as opposed to the original data. As opposed to this, we're going to take the Fourier transform of it, multiply by a Ramlock filter, go back to space, the spatial domain, which is now a filtered projection. It's no longer just a projection. We'll back project those. That turns out mathematically to actually be the correct way to get the coefficients out. Another way of doing it, because this is essentially the multiplication in the Fourier domain is equivalent to convolution in the spatial domain. Those of you who took 280 will remember this. So you can convolve this with the inverse Fourier transform of this Ramlock filter, which looks something like this. Take the convolution of those two things, take the convolved projections and back project those to get the image. So let's look at what happens to a projection that looks like this, right? This is that disk again, or an ellipse. What happens after we do this filtration on it to get to this point, this convolved projection, right? Or the inverse Fourier transform of this, which again is that convolved projection. It looks like this, right? Which doesn't look anything like this, right? So the projection is fine, but once you do that convolution, you essentially then get an object that has a flat top, which is good for reconstructing something that has a flat top. and it has these negative side lobes around edges, right? And so it's quite a different function than this one. When we back project these, we can actually reconstruct the correct final image. So this is the sinogram of the raw projections. This is the sinogram of the convolved projections, right? Those ones that have had the convolution passed across. When we look at the values of the projection versus the convolved projection, here you can see the projections are all positive numbers, which makes sense, right? Here we've got something that's centered around 0 and has a lot of edge information in it. So we're now going to back project this function instead of that previous one we did. And after 40 projections, we get this. After adding in 80 projections, we get that, 120. And then by the time we're done at 240, we get the original object back, okay? And so this is a movie of back projecting these convolved projections and adding them all up to create a picture. And so that's how a CT image gets made, right? So we have initially that projection plus another one, plus another one, plus another one, plus another one. And you can see this edge is well resolved because all of these projections are kind of going down this way. Edges up here they're not resolved at all because we don't know yet. Like, we don't really have any information about an edge up here. By the time we get around to 90 degrees, we do now have information about these edges. And so this is consistent with all of the projections that we've got thus far. And then we keep rotating the detector around, adding in those projections. So this is convolution back projection. First, you take your raw projections, convolve it, right, with the Fourier transform of the Romlock filter or a different kernel. Some of you will have projects that involve different kernels that change the smoothing of this processing. Okay. And this again is just that pointing to that MATLAB program. You can replace those little dots with something that looks like this. This is a famous phantom used in CT and medical imaging. And it basically is just a set of ellipses overlapping. But how that gets reconstructed can be used to demonstrate different things in CT. Oh, we have a question. You can just speak out. I think I can hear you, Nasheen.
Uh, yeah, so regarding the filter, is it always a Ramlock filter or like there are other options?
That's a great question. It is not always a Romlock filter. In
Okay.
fact, the Romlock filter works very well for noise-free data. And so if you're doing mathematical things, the Romlock filter is the correct filter to use to actually reconstruct all of the precisely correct values.
Hmm. Okay.
However, the Romlock filter also amplifies high frequency noise considerably. So if your data has noise on it, which all data will when it's taken from a
Hmm.
human, using the Romlock filter will produce very noisy pictures. And I think I have some examples that I'll show you. And so rather than the Romlock filter, you use a modified Romlock filter where it still goes down to 0 at the origin, but it doesn't keep rising up, up, up as you go to high frequencies. It comes up and then you roll
Hmm.
it off. So it starts
Okay.
looking more like a smoothing filter, and that's
Hmm.
called the kernel of the reconstruction. And it is something that there's a lot of lack of understanding, I would say, amongst clinicians who do CT about the effect of these smoothing kernels. The
Hmm.
pictures can look a lot better when you use a kernel that does a lot of smoothing, but it certainly gets rid of spatial resolution, right?
Hmm. Yeah.
Your ability to resolve two objects that are close together goes away. And so I think some folks are doing projects that will demonstrate in CT, the effect of different
Mm.
kernels.
Okay. Oh, thank you.
Uh, sure. So talking about measuring spatial resolution, one of the things we want to establish for a protocol that we're using, if the clinician likes the pictures and they're comfortable reading the pictures, then normally that is the criteria that is used for setting what kind of filtration you're going to use, right? And whether or not you're going to use a Romlock type filter or one that's a lot smoother. So the procedure I would say that happens is you just iterate with a clinician until they get comfortable and they like the appearance and the feel of specific filters or kernels, as they're called. And then you have to go in and measure and ask and really establish like what is the highest spatial frequency we could measure with that reconstruction or that kernel. And that is what is the signal that changes as a function of space. What's the shortest wavelength that we could actually measure, right? And you can do that with phantoms. And some of the phantoms you can put in to the scanner look like this. They're just parallel bars. They can be metallic bars in a plastic background. And they just get closer together. And you image this pattern, and then you look and say, okay, by this time I can't see those bars anymore. That's my cutoff frequency. That's the highest spatial resolution I get is when I can see it. Or you can create a shape like this that's more continuous, and then there'll be a point at which you just really can't see it anymore. So here's an example of a phantom, excuse me, that you can purchase for like $10,000 or something, maybe even more, that has separated bars, so they're separated by a specific gap, and the bar itself has a specific width. And then we look through and we say, okay, by the time I get here, I don't see bars anymore. So this is basically my threshold for spatial resolution, maybe even this one, right? This is where it really starts to cut off. And so at this frequency, or cycles per millimeter, that's where this thing's cutting off. And this is using Fourier back projection or filtered back projection with whatever the chosen kernel is. They say it looks like this. This paper, if you go to this paper and read it, these folks come up with some other type of iterative process to make the reconstruction in which they say we preserve more high frequency data without having the noise explode, and we get a better looking picture. It looks like this. So you compare this to this and you say, oh yeah, your troughs here are deeper. Therefore, the spatial frequency is coming through more clearly with your reconstruction. And that's a very empirical way to measure spatial resolution. And we have phantoms here that we got made in the machine shop that have another way of doing this by just imaging discs, which reduce their diameter. And so we just drilled smaller and smaller holes. And then what you do is you look at the change in the contrast between the hole and the background as the basically as the hole gets smaller. And essentially the contrast will eventually go to zero, right? Until finally the hole's so small you can't see it. It's the same amplitude as the background. I think you guys used that phantom to look at modulation transfer function. You have a sequence of holes and you measure the amplitude of the variation, and then as the holes get closer, it reduces down. So in practical terms, what we want to measure is essentially the components of a coronary vessel is a hot topic. Like we would really like to be able to zoom in, measure the wall of the coronary vessel, the lumen and calcium, and be able to say what are the components of this lesion. And this image was obtained on a colleague's tabletop CT scanner, in which he can make very high resolution pictures. And so here's, um, this is well, actually, I stand corrected. I think this is in a clinical scanner. Is that right, Phantom Indy? Yes, it is. This is in a clinical scanner. We'll see his picture in a minute, but we've got a 500 micron slice, so a very narrow slice, looking at this coronary vessel. This is a human heart that was taken out as a pathology specimen and placed into this preservative called formalin. And we use these actually to measure with MR, I think, the fiber direction of various tissues. Plus, in CT, we looked at these coronary vessels. So here is the image of this vessel. This is the wall. This is the basically the lumen of the vessel, in which there's this element called formalin in there, and this is a piece of calcium. These two images are absolutely equivalent, except for the fact that we changed the amount of current in the X-ray tube by just 1 milliamp, and it flipped the tube when we went to this higher current. So it's essentially equivalent. It's 1 milliamp higher, but it flipped the spot size on the X-ray tube. So now, instead of a small spot size, it opens the spot size up, and the electrons hit a bigger target to make more X-rays. And so, if you wanted to go to a higher, fluence of X-rays, you would be over here going higher, and the spot size would remain large. And it shows the effect on the resolution of changing that spot size. It's very subtle, but it's there, such that the little t here is much taller than, there's no t here. It gets smoothed out, and the amplitude goes down a little bit. And that's just smoothing from the source of the X-rays, the spot size getting bigger. Pretty subtle, but basically compared to changing the reconstruction kernel from, the Romlock kernel to some other kernel. But here you go. The MA went from 430 to 440, switched the auto spot, and we get a blurrier picture. These, okay, so now we're on to images obtained by my friend's tabletop scanner. And so here you can see the pixels get really small. This is the wall of the artery here. The contrast has gone down somewhat. And this is the piece of calcium, right? And then this is the lumen. So you can actually see tissue between the calcium and the lumen, which on the clinical scanner we could not. So that's what it looks like on resolution from a clinical scanner. This is the underlying ground truth from this tabletop bench scanner. So the reason this has much higher resolution is the detector that was used has just more pixels on it, and the heart was zoomed up to fill that whole detector. Whereas on a clinical scanner, we're kind of stuck with the geometry that we use for humans. Okay, so looking at this as a coronary, like, oh man, we're right on the border of being able to say really, confident statements about what are the components of the plaque, right? So we're right on the border there. And the new photon counting detector scanners, and if there is, a desire to really quantify these plaques, you have to lift the dose up. You have to use more photons to make better pictures. So you lift the dose back to what it was about 5 years ago, 10 years ago, and you'll get better pictures. But we'll see some of that. So remember about the MTF. So if I have any kind of function, right? A 1D function here, just from simple Fourier analysis, can be created by adding up a set of sinusoids and cosines, right? You learned this like probably in freshman math, right? So this is called a Fourier series analysis of basically a periodic function. So these high frequencies are required to make these hard edges on things that you want sharp pictures of, like things that have high resolution, right? And you can quantify how the system responds to different spatial frequencies in the pattern. And so if I have a frequency here, uh, and I measure how much power or amplitude gets through my imaging system, it gets reduced by 4%. At this frequency, it gets reduced by 15%. This one goes down to 32% reduction, et cetera, until finally at high frequencies, basically not much of the energy from this gets through. It goes down to 7. And though that relationship between the relative amplitude that gets through the imaging system to the spatial frequency, that's called the modulation transfer function. And eventually you hit a spatial frequency where nothing gets through. It basically just looks like a mean value. Even though you have a sine wave there on your picture, when you image it, you just get a mean value of that sine wave, no oscillations. So this is a way to characterize the performance of your imaging protocol. You can image a phantom and you can measure this curve with protocol 1, image the same phantom with protocol 2, and then plot the two MTFs side by side and say which one is better, right? So does it matter that I'm using deep learning, to denoise this? What happens to my modulation transfer function after I apply deep learning to the picture to smooth the noise? Do I still get the same edge response or the same modulation transfer function? Probably not. It probably, rolls off a little bit sooner such that it's a bit smoother, right? But if it's an amazing deep learning denoiser, maybe, it sticks pretty close. So the modulation transfer function is in spatial frequency space. Basically, you can also look at the point spread function, the line spread function in the imaging space. So if I have a really tiny dot and I image it, it comes out looking like this, and I can measure the width of this function. And so my full width at half max of this is a method of reporting spatial resolution for the system. Uh, if this is a Gaussian function, mathematically, I know that the modulation transfer function, given that this is the point spread function, is a Gaussian function. And I know I can derive it analytically. It is the Fourier transform of this function. So the two things are related simply by the Fourier transform. So often you will see resolution reports giving the modulation transfer function, and it'll say, we reach 10% at this spatial frequency, right? And that tells you how wide the modulation transfer function is. Another way is just using the full width at half max of the point spread function. Okay, so that is the technical stuff with CT. Now we're gonna take a look at some of the applications. Here we go.
I just got one more question.
Sure, go ahead.
So MTBF and then you said the line spread function, these are like the two methods to show the spatial resolution, right?
Correct. If you want to classify the spatial resolution with a single number,
Hmm.
right? So you want to give somebody just a number, then oftentimes the full width at half max of the point spread function is the best way to do that
Hmm.
because it's quite intuitive, right? So, say the full width at half max is 1.2 millimeters. Then sort of that a perfectly clear picture would just get convolved with a 1.2 millimeter wide Gaussian, and that would make the image.
Yeah. But
Right?
wouldn't that be a more crude way of saying it? Like, wouldn't MTBF be more like detailed in a way?
It is, especially if it's not a Gaussian function. Okay,
Yeah.
if it's a Gaussian function, then you can just give one number, which
Mm-hmm.
is the full width at half max of the MTF, and you know
Yeah.
analytically every other number given that.
Yeah.
If it
Okay.
isn't a Gaussian function, if it has, say, a long flat top and then it rolls off, right, which some filters will produce a sort of flat response and then they roll off, then you might give the roll off shoulder of the MTF and say what it looks like.
Yeah.
Um, so that's if it's more complex than a Gaussian, then the MTF is
Mm-hmm.
useful.
Okay. Okay.
And nowadays, everything is reconned and filtered with AI and deep learning. And so the only way, so we've given up on using linear systems to just predict what the spatial frequencies will be or what the spatial resolution will be. You actually have to measure it now. You have to put a
Oh.
phantom in, do your deep learning on the picture that comes from that phantom, and then make measurements, right?
Mm-hmm. Yeah.
And so that's made it more arduous in a way, right?
Mm-hmm.
But the the good news is some of the deep learning filters to reduce noise are remarkably good in that they preserve edges very well. They don't just uniformly blur, they march around and they say, you know, this patch, it's all liver. I may as well just make it liver. So just like they'll smooth that in, right?
Mm-hmm.
And then so you get these spectacular looking pictures. It looks like you use 10 times the dose or something. But
Oh.
then you know you have to be careful because when you get to small objects, is
Mm.
it the true object, right?
Yeah. Yeah. Okay.
So these are all cool topics that are hot right now.
Thank you.
Okay, so we're going to look at applications. First application we'll look at is coronary angiography. And this is a huge thing, right? Because you can, with an essentially non-invasive technique, somebody comes in with chest pain, you can tell them in 20 minutes, do you have coronary artery disease or not, right? If the person is, say, 52, they might have perfectly clear vessels, right? With no calcium, no lesions, nothing. So whatever is causing their pain is not heart disease, right? So you can just send them home. And in England, that's what they do. Everybody who comes in the hospital with classic chest pain, classic ischemia symptoms, they get a CT. First thing that happens. You don't keep them overnight, put them on a treadmill, do all this kind of stuff. You just get a CT because half of those people you're just going to send home, right? So it's much more efficient. And part of the reason is this is the image quality. This is from 2015. So this is like 11 years ago, image quality. Uh, this is this triangle here is fat. Inside the fat is a bright coronary vessel, which you know has a measurable diameter. Uh, that's this plane right here. So we cut this image down this plane and we get this cross section of the artery. So we can see it's wide open, right? We now cut this plane down here and we see that, well, there's a little dot there. That's a piece of calcium, right? And it's not perfectly round. It seems like there's some kind of something's pushing in on this. So there could be like a reduction in the diameter of the vessel. This is the left main. This is pretty far up. Then you look down here at this one. So this is the LAD coming off. And look at the diameter. It's quite a lot smaller, right? So this did narrow down getting out into the LAD here. So this could be something to keep an eye on for the future. But this is all obtained in one, or actually this looks like Siemens data because of this filtering and smoothing. It looks like somebody combed the noise, right? It's fascinating what different manufacturers do to make pictures look better. Um, it is certainly not random noise when you look at it, right? So, um, I guess this given it this was a Siemens force, it was probably done in like 3 heartbeats, something like that. And for this patient, every heartbeat probably was the same. There doesn't look like there's any motion artifact. The other thing that you can do with CT, and this has been done for now 25 years, and so there's a lot of data supporting this, is that you can do a calcium scan. And a calcium scan, essentially you don't need a contrast agent injected into the patient. You just get them to lie down. You put ECG leads on, take one quick picture. It doesn't usually take multi-beats, but one quick picture with no contrast, and you will see in some people these bright signals in their vessels, in their coronary vessels, and that's called coronary calcium. Each one of these patients is shown here have absolutely equal predicted risk of having heart disease. Before they got in the scanner and we knew what was going on, given their age, their history, each one of these people has absolutely identical risk of having coronary disease and dying of a heart attack in 10 years, over the next 10 years. When you do this, you see this person have absolutely no indication of coronary disease in their heart. This person has calcium value of, it looks like 10, I don't know what it is. Yeah, it's 100, sorry. And this person has a calcium score of 400. And the calcium score, you just basically add up all the calcium. It's got its own formula, but it's essentially proportional to the amount of calcium. So now each one of these patients has a remarkably different amount of risk for having a heart attack in the next 10 years, right? And it's been shown super clearly that people who have this middle risk, they're sort of 50 to 65. So you're kind of uncertain. So you say, what's the detection task for calcium? For a patient with somewhere between 5 to 20% Framingham risk score of having an event, of having a heart attack in the next 8 years. Okay, so those are the people we're going to bring in the door. And then when you do all of these tests that have been invented to try and predict who has more risk of having a heart disease, and there are a ton of these have been done. Their blood tests, their vessel pressure tests, their intima media thickness measurement, all of these things have been proposed. Really, only one really pushes the ROC curve up to the top right corner, and that's coronary calcium. So if you say, when I change my sensitivity threshold of saying, oh, you are going to have an event at different levels of coronary calcium. So I get a very high sensitivity if I say, if you have any calcium at all, I'm going to say you're going to have a heart attack in the next 8 years. I'm going to pick up 90% of the people who do have a heart attack. But I'm also going to include 60% of the people who don't in my prediction. So that's not a good spot, right? So at calcium 10, don't do that. At 100, I still pick up 85%, and I'm now down to a 40% false positive rate. At 400, I'm down below a 20% false positive, and I get 60% of the people. So there's a lot of noise. Biology is noisy. Some people survive heart attacks, and they don't even know they had them. But when you do the ROC curve, it is the only test amongst all of these that really pushes the envelope out. And so now the American Heart Association recommends it. All the major societies recommend that, you should have a calcium scan in your 50s. I think you should have a calcium scan in your 30s, actually, because some people, it turns out, do have calcium in their 30s, and those people should go on a statin right there, right? At that age. Trying to get my arrow back. I don't see how. Okay. So another way of evaluating risk is to look at the the nature of the lesion in terms of its ability to stop blood flow. And this is called basically this FFRCT. It was developed uh, using a computational method to simulate actually having a measurement done that's done with a catheter. And this FFR catheter goes into the vessel. I think, I don't have a slide on it. But anyway, the FFR catheter goes into a vessel. If it crosses a lesion and then it measures the pressure on one side versus the pressure on the other. And if there's a large pressure drop across that lesion, and that pressure drop is more than 20% of the pressure in the aorta or, proximal to the lesion, then that patient should probably have a stent put in. And there's a large trial done showing that the people who didn't have stents put in showed up at the hospital in an emergent situation much more frequently later. And so it led to this measurement, FFR, fractional flow reserve, it's called, which had been around for 30 years. It led to that being a deciding criteria for whether or not you got a stent, okay? As opposed to just a cardiologist looking at the picture and saying, I think you need a stent. So the interesting thing is a person at Stanford, Charlie Taylor, who did computational fluid dynamics or does computational fluid dynamics in vessels, did it in the coronary vessels. Given the fact that we now have high resolution coronary CT, you can create a vascular tree that's a model of the patient's coronaries. You also have a model of their myocardium. So you know how much tissue is required to be perfused. And so given those two things, you can use computational fluid dynamics to predict how much blood flow would go down the vessels given a dilation. If all of this myocardium needed blood, how much blood flow would come down here? And then from that, you can measure the pressure or predict what the pressure drop will be. So they did this. It's called heart flow. And then they compared it with the catheter measurement, and it actually worked out really well. And so they started a company, and HeartFlow's now been in business probably, say, 10 years, that a lot of people have been using it. And you essentially send your CT data to HeartFlow. They do a lot of calculations, segmentation, and then calculations, and they send back a map that looks like this, and it tells you whether or not a stenosis is critical. And and it's when radiologists and cardiologists are on the fence, they look at a lesion, they go, I don't know, doesn't need a stent, does it not? You can do this, just push this button, data goes off to HeartFlow and it comes back. And it's been shown to actually save a lot of money due to the reduction in unneeded stents being put in. So the applications that we're looking at today are you would like to be able to look at a lesion in a coronary vessel and understand its composition. Does it have fibrous tissue in it, calcium? Is there essentially a lipid pool in there that has a low attenuation, showing that's actually a pool of lipid? Another function that you can do with CT is when you're injecting the contrast agent, you can look at the amount of contrast that goes into the tissue, all right, just by looking at the signal in the tissue. This, unfortunately, for CT is a lot noisier than it is for MR. MR, these perfusion maps are pretty spectacular, and so CT is lagging there. Function, which means how is the heart wall contracting? Is it contracting normally? Do I get normal myocardial shortening and strain at every position in the heart? And you can make very beautiful global and regional myocardial strain maps using both CT or MR. You can do it with MR. Echo, you get it just by looking at the deformation of the heart in real time. You can do signal processing with the echo, but yeah, it's a little noisy. And then CT is used a lot for procedure planning. So if you're going to get a new aortic valve put in your heart, first thing you want to do is go get a CT and see how big is, the root of your aorta. Like what size of valve am I going to need? Is there anything in there that I have to worry about, like calcium? Is there a lot of calcium on one of the valves? I need to take it out. And so that basically over the course of these transcatheter aortic valve implantation development, CT went in lockstep with the development of that technology, and it's used all the time. Nobody gets a TAVR without a CT, basically. LAA closure. So if you have atrial fibrillation and you're concerned that the blood is pooling in the left atrial appendage, you can close off the left atrial appendage with a device called the Watchman. And initially, it was only guided by transesophageal echo, but more and more, at least at UCSD, the clinicians are saying, we've got a CT scanner, we should take a CT of the LAA because we get such a nice picture of it, so we know exactly the orientation and the size that we need to put in there. And so that's used. And then every patient who gets a treatment for atrial fibrillation, which is burning the tissue or killing the tissue around certain targets such that the aberrant electrical activation that's occurring on the left atrium goes away. That's, a 4-hour procedure in a cath lab where you have a catheter and you're burning bits of tissue. Every patient that goes for that procedure initially has a computed tomography scan and a 3D model is built of their heart. And then as the procedure goes on, they paint onto that model what they've burned. And so they know how to what to burn next. Okay, we did this. We don't need to do that. Okay, so here is sort of a rogues gallery of different coronary CT images. And so first, calcium, totally observable in a non-contrast scan. Even when you have very tiny bits of calcium, you can detect them. And we have a paper on how small they can be to detect, and they're really small. This is called soft plaque, which I have a vessel which is pretty wide open. It's not going to change the flow, but it is developing this lesion there. So there'll be some inflammation and it always carries the risk of the endothelial layer here being damaged by the plaque and opening up even just a tiny little exposure, and then you get a clot, right? And so if you have this soft plaque, you can still die of sudden death by this thing just tearing a little bit and making a clot really quickly. So it's good to know that they're there. Here we have soft plaque with essentially a calcium signal there. So there's a little tiny piece of calcium in there. As you can see, it's challenging the spatial resolution of the scanner, right? You don't really know how big this piece of calcium is. You just know that it's like a blob, right? The PR on here is what's called positive remodeling. And that is the great thing about CT is we can see not just the lumen like in X-ray angiography, we can see what's outside. And so you see that the edge of this plaque has a bump on the outside of the vessel. And this one too has grown the vessel in this direction. And so that's called positive remodeling. It's a characteristic which carries heavier risk. Heavy calcium's pretty obvious, heavy calcium and positive remodeling. This is low attenuation plaque, this thing here. So we have the lumen of the vessel. This could be lumen or a small piece of calcium. You don't really know. You could know if you did, sort of dual energy or uh, uh, photon counting CT in which you looked at different energies. And then you have this dark signal right here. And the dark signal is called low attenuation plaque. And it is assumed that the signal, if it reaches a certain darkness, it must be fat. There must be a lipid inside there. And that carries additional risk if you have that. So here we have low attenuation plaque, positive remodeling. This is the lumen here, a really large piece of calcium, lots of disease going on here. It would be better if we had, say, twice the resolution, right? Because this thing looks a little blurry. Granted, it is the coronary vessel, right? It's a small object. Think back to nuclear medicine. We were getting these blurry pictures of the whole ventricle, right? Now we're complaining that we don't have enough resolution from CT to get the coronary vessel, right? So we've made great progress, but still, I think we can do more. This is called low attenuation plaque with napkin ring sign. It's pretty funny, right? So there's a ring around this lumen here. This is called the napkin ring. And then inside here is this low attenuation plaque, presumed again to be lipid. Now, remember, you can make negative signal, right, from CT through artifact, through, basically motion, some beam hardening, a streak from somewhere else. So you have to be careful to say, oh, I know this is fat. You really want to confirm that the imaging protocol you're using has the ability to resolve something that small, right? And that's where testing resolution with phantoms comes in. You say, if you see clinicians and they're calling this and say, that's low attenuation plaque, and then you go look at your phantom and say, I can generate those in a phantom that doesn't have low attenuation plaque, then you want to be careful. So we're right on the hairy edge right now of the resolution required to make all of these calls. And here you can see this spotty calcium here versus a large chunk of calcium. All of these things apparently can modify the calculation of the risk for this person. And however, you have to keep in mind, you see all of these features and you say, okay, here's your risk. You're really only going to do this one thing to these people. You're going to put them on statins, tell them to quit smoking, tell them to get some exercise, right? That's basically it. So as soon as you see any of this stuff, you should just go on a statin. Here's what a stenosis can look like on CT. And, the risk of having a acute coronary event with a stenosis that's greater than 50% is a lot higher than those people that don't have the stenosis. And so it does carry risk, or it's like a factor of 34 versus not. Here, this positive remodeling signal is carries additional risk, as does lipid inside the lesion. There's a napkin ring sign, etc. And so you can look this paper up if you like about all of these relative risks that go with these features. Okay, so as engineers, like, we design protocols and we design imaging devices such that they produce images that are the same over and over, right? And you really don't want a device in which the imaging protocol or the imaging study fails due to some engineering problem, right? So here, if you look in literature, here's a paper and say, well, how many coronary segments, when we look at them, does the physician look at it and go, that imaging quality is not high enough. I can't read that. So in this study, it wasn't that high. There was 202 out of about 7,000 segments, right? So 3%, you're just not going to be able to look at them. Well, when you look at it per patient, on the other hand, it goes up to 15%, right? And the reason for that would be that the certain patients are harder to read than others, right? And a lot of that has to do with how large the patient is, because if the patient gets larger, the number of photons that can get through the patient drops, and so the image quality drops down. And so anytime you're imaging phantoms, this is something to keep in mind. If you just put a phantom in the scanner on its own without anything around it, and you take pictures of it, they will look spectacular. They look absolutely beautiful. And the reason is, what you just ask, well, why do these look so good compared to my clinical scans? Clinical scans are, the thing you're looking at is surrounded by a large human. So you need to essentially simulate that. And so we have these rings that we put around our phantoms that reduce the number of photons that actually get to the phantom, right? And then common motion artifacts, either the patient's breathing or the cardiac gating messed up, or heartbeats weren't the same. If you needed 3 heartbeats to get your picture, say you're on a Siemens scanner, and one of those heartbeats was a bad beat, that kind of screws up the thing. Coronary calcium gets in the way in terms of there's just too much calcium to see underneath the calcium. Like the calcium is a very large signal, and then it sort of spreads out over the vessel. You can't see it. So here's some image quality examples. This is what an image looks like when you use 700 milliamps of current on the X-ray tube. And then for this same patient, as the X-ray tube was being turned off, we continued to image, right? May as well use those X-rays, even though there aren't that many of them. So by the time we get down here, we're down at 70 milliamps of current. So 1/10 the number of photons is here. And that's the comparison of the pictures. So you can see there is a difference in the background noise, the amount of hash on the scan. But also when you look at the difference between this picture and this picture, the Hounsfield units should be the same, right? So the mean value in the ventricle here and here should be the same. And when you take the difference, that turns out to be true. Everything's centered around 0. But there's structure to this noise, right? You're looking at it and saying, well, wait a minute. This isn't just a random noise field. There's structure. And that's because these edges, right, stop being resolved as well. And so if we look at a really sharp edge, like up here versus up here, you see the difference in the difference picture. And so high frequency features tend to get washed out when you start losing photons. And the reason for that is that the manufacturer, when they look at the sinogram that produces this, the sinogram itself doesn't look good. And they say, oh, we need to fix this. We need to smooth it. There's even detectors that have too few counts. We need to paint artificial counts in there just so that the noise doesn't totally explode. And in doing all of that machinations, you lose spatial resolution, which, is not from first principles what should happen. First principles, basically, if I have 1/10 of photons, I should have the square root of 10, right, times the noise over here, right? The root mean square deviation should just go up by the square root of 10. That approximately happens, but not as quickly as the square root of 10, right? And because they do smoothing. So here, if you were to say, can I use this picture? So this is an ultra low scan. This would be way, way less than a millisievert, like 1/10 of a millisievert or something. Can I use this picture for anything? Right? Why get this high dose well, high dose? This is a low dose picture, but why get the one that's, at 700 MA? If all I need to estimate is the volume of the left ventricle, this is fine, right? When I take that volume, I'm going to be within a few percent of that. If, on the other hand, I need to look and see what's the diameter of the left anterior descending coronary artery, I look over here, that's not going to happen, right? So depends on the application, what you need. So here, if I need to see the struts of this stent, that's not going to happen over here. So the big difference is in that super high resolution estimate of this coronary stent. So there you can see that smoothing that occurs when the quality of the data goes down. These are classic motion artifacts. So when the heart is beating, we'll just over the over the course of one R to R interval, so we have a QRS, trigger the scanner, and then another QRS, we stop scanning. So we've scanned over the whole heartbeat, right? And we keep the scanner rotating like this, and we will just take data every 150 milliseconds and make an image. And so then that will, page past us at about 7 frames a second. And here's what the pictures look like. We see the ejection of blood, we see the motion of the myocardium, and we see the coronary arteries. So this is the right coronary artery up here, this is the left, and you can see the motion artifact associated with imaging that coronary artery while it's in motion. Okay, so look, it looks almost like it's a cycloid artifact, right? So in one, there's this big streak, the artery turns into a streak, and then there's another where there's this cycloid artifact. A lot of it depends on what is the orientation of the projections being obtained at the peak of that motion. What direction is the motion in? And is it like this motion is going this way? So if I'm projecting data this way, that motion is going to streak along my detector, right? If, on the other hand, I'm looking at a project, if my detector is over here and I'm projecting this way, when this moves up and down this way, it doesn't really change its position on the detector, right? So you have to know what is the relative position on the detector of that motion as it's occurring. And then here, this is an example of using motion correction by taking the raw data, putting into your reconstruction a model of how things are moving, right? So this is the coronary artery, it's moving up and down. This is an axial slice. This is without that model and just reconstructing, assuming the object is stationary. And you can see the image quality difference here. So let me, oh, good. So at some phases of the heart cycle, like here, the heart's pretty static, right? It's pretty stationary. And so you get a really good picture even without doing motion correction. However, at certain phases of the heart cycle, like this one, you can see that the vessel is spread out over some distance. Whereas in the motion corrected one, we have a model where we say, okay, for all the projections around here, we know it's moving from here to here. You put those together and you can correct that motion. And so there at end systole, we get another sweet spot where there isn't a lot of motion. And so some folks would say, why do motion correction? Just wait till you get to a position where the motion artifact goes away. And my answer to that is, look, we can do motion correction. We should always look at these movies instead of these ones. Let's just do the motion correction for all of them. And that's pretty well what's done at this point. Okay.